Our first presenter of the night is Dr. Jennifer Klay. She was a postdoctoral fellow and researcher at Lawrence Livermore National Laboratory before coming to Cal Poly. She leads two efforts, one in high-energy nuclear collisions and one in low-energy nuclear fission. Her presentation is entitled Truth and Connections, A Human Quest Through Particle Physics. Please welcome her.
Thank you. It's a pleasure to be here tonight to tell you a little bit about what I do. And I want to start off by just saying that when I was asked originally to participate and they told me what the theme was, I had to really think about how I would approach that question. And how I'm going to answer that tonight kind of is reflected in the title I chose, Truth and Connections, A Human Quest Through Particle Physics. So what do I think it means to be human? Well, you know, when I thought about that, I put myself in the place of what do I, as a human, strive to do with my life. And the two things that I would say I've devoted myself to are these two things, truth and connections. So seeking truth through scientific inquiry is the basis of my career. And then seeking connections through family, friends, and so forth. So what I want to do tonight is actually just tell you a little bit about how I would define those two topics or themes. And then I want to put them in perspective of what I do in my career, namely explain a little bit about particle and nuclear physics, what we're trying to understand about the universe, and how we do that. So that's going to be maybe the bulk of what I talk about. And then I want to kind of step back for a moment and think about popular conceptions of scientists, in particular in science fiction, the portrait of the mad scientist, and some of the speculations about the kinds of science we do, and on whether or not, for example, the Large Hadron Collider could destroy life as we know it. So discuss a little bit about black holes and antimatter bombs. And hopefully by the end you'll be reassured that we're not about to be destroyed by this path through scientific exploration. And then kind of wrap it up by humanizing that mad scientist caricature. And I have a few concluding thoughts. And then what I'd really like to do is have a discussion about what you think, about what you've heard, and also what you think it means to be human. So if we start by just pondering the idea of truth, you know, the sort of dictionary definition would be the quality or state of being true, that which is true or in accordance with fact or reality, a fact or belief that is accepted as true. And we have to kind of agree on what we mean by a fact. And I like this quote from Einstein, where he said trying to put this a little bit in perspective about how we think about these things, that what I see in nature is a magnificent structure that we can comprehend only very imperfectly, and that must fill a thinking person with a feeling of humility. This is a genuinely religious feeling that has nothing to do with mysticism. So I find this quest for knowledge and understanding what we know about the universe to be sort of a humbling part of putting me in my place in the universe. And it's as he said, sort of a religious experience of its own kind. I think seeking truth is really a fundamental human endeavor. And if we're talking about scientific truth, there is a path that we as scientists take to try and explore it. First off, we make observations about the way the world works. And then we try to explain those with a hypothesis. And hypotheses are sometimes correct, and they're sometimes incorrect. And what we have to do is figure out how to arbitrate the correct ones from the incorrect ones. And so we test our theories about how the world works through observation and then refinement of those hypotheses. And if you think about it, if you consider someone from, say, 200 years ago or even 100 years ago stepping into our modern world, they would certainly be shocked at what they saw. And this quote from Arthur C. Clarke, I think, kind of sums it up, that any advanced technology, any sufficiently advanced technology, is indistinguishable from magic. But it really is true that someone coming in who didn't have the background would be surprised by what we're able to accomplish. But with a little bit of study, you can actually see that there's a perfectly obvious path from that point to this point that we can actually attribute to scientific exploration. As I said before, the way we try to explore scientific truth is through experiments and observations. We make hypotheses, and one of the important ways that we test our hypothesis is that we actually make predictions about what they would say about the universe once we've made a hypothesis, and then we design experiments to test those, and we keep going. And the process is, I show it here as a circle, but I like to think of it more as a spiral. And the two types of people that engage in this, you could almost break it down into two categories. There's theorists, the people who try to propose the hypotheses and make predictions about the world, and experimentalists. And those are the people who design and conduct experiments and present the observations back to the theorists for them to help explain. And by way of explanation, I myself am an experimentalist. So when a theorist tells me there's a new particle, you should go look for it. Can you build a machine to do that? Well, not me personally, but groups of dedicated and like-minded experimentalists who get together and decide they would like to look for something can, if given enough resources, do it. And that's what I'm going to talk about this evening. So as I said, I think the path towards truth is really a spiral, and the direction that we take is unknown when we start the quest. So if we imagine sort of this spiral as our path, continuing that inquiry I mentioned before, where we start with an observation, we make a hypothesis, then a prediction, and conduct an experiment, we're always hoping that the spiral sort of decreases in size to smaller and smaller refining questions until they lead us to a theory or a law that emerges to guide us to a deeper understanding of the universe. And from that, we can say something, we can manipulate the universe and say something about how what we do to the universe actually impacts it. But because we don't know what we're looking for, oftentimes, if we start at a particular question or a particular observation, and we make a hypothesis, and we start pushing on it, it actually leads to bigger questions. And so the spiral gets bigger, and the question can remain open for discovery. And there are, important questions that people like to ask. When I say I work in particle physics, well, what happened before the Big Bang? And some of these things, science just does not have an answer for. And we just hope that maybe someday we can come up with a way to think about the universe that sort of minimizes the number of dark corners that we can't know anything about. But as scientists, we also have to accept that sometimes there are things that we cannot fully grasp. And I like this second quote from Carl Sagan, where he said, "It's far better to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring." So as a scientist, we always have to accept whatever the findings are and move on. And sometimes that means changing your field if you find that a particular area that you've been looking through doesn't really have answers that you can ask experimental questions about. So that's sort of my take on truth, or how I'm going to approach the question of truth for the purposes of this presentation. And now I want to talk a little bit about connections. And we heard about some of this in the answers to the question that were posed to people on the street. I think it's fundamentally human to seek relationships. We have family, we seek out friends, colleagues. As a teacher, I also have relationships with students. And all of those are something that I can't explain scientifically, but that we have this desire and need for those kinds of connections. And we want to be known and acknowledged, not just for who we are, or I should say it the other way. I would say for what we do, but also just for who we are as being a human being on this earth. And I think we also strive to leave lasting legacies. So for example, we have children. Maybe you have noticed I myself am pregnant and having two children, two twins in the summer coming up soon. And that's one way that we connect. We pass on our ideas, our personal sense of the world to our children through our family. And when we leave this earth and we pass on, we hope that we've connected in some way to people in a way that leaves some idea of who we were in their memories. And we do that through our personal connections. But that lasting legacy for the personal connections is only going to reach 1 or 2, maybe 2 generations. Some people are fortunate enough to reach 3 generations. And I think that many of us also look to leave a lasting legacy in terms of the things that we do. So the discoveries that we make in science, the art or letters, the books that we write, the words that we write, that can pass on, or even the service that we do to help our fellow human beings. And then, like I said, because I'm a teacher, I think teaching the next generation what we've learned, passing on that knowledge, is also an important part of leaving the legacy of the connection of I was here and I did something for the rest of humanity. Okay, I'm going to take now, that's kind of setting the stage for the 2 themes I'm going to explore throughout the rest of the talk. But now we're going to move into what I would call the scientific content of the evening. And I hope you'll stay with me for it. We're going to start by talking about exploring the universe through nuclear and particle physics. And in particular, I'll begin with the particle model of matter, which really sort of began at the start of the 20th century. As only about 100 years old, our understanding of matter as being composed of atoms, and the atoms are actually composite particles that are made up of a nucleus, a positively charged nucleus at the center, and negatively charged electrons orbiting around it. And this is 2011. It's actually the 100th anniversary of the discovery of the nucleus by Ernest Rutherford in 1911. A few years later, about a decade or 2 later, they realized that the nucleus itself had a substructure. Rutherford sort of was the one who proposed the idea of this positively charged proton, or the core of a hydrogen atom, if you will. And Chadwick came along about 10 years later to explain, by positing the existence of a neutron, the rest of the phenomenology around what we saw in nuclear interactions. And that led us to this model of matter where even the nucleus is not a fundamental particle, but it's composed of others. And another 3 or 4 decades and many, many more people to work on this later, we realized that the proton and neutron are also not fundamental themselves. They are composed of smaller particles, which we, thanks to Murray Gell-Mann, call quarks and gluons. So the gluons are basically the binders that hold the quarks together. And in most matter, such as protons and neutrons, what we see are 3 quarks bound together tightly. As beyond that point, after 1968, when we discovered the idea that quarks existed, the standard model of particle physics was sort of born and began to take off. And we've actually spent it took another 30 years to fill out our understanding of what you would almost think of as the periodic table of the standard model of particle physics. There's 2 classes of particles, quarks and leptons, and in each, for some reason that we have not yet been able to explain, there are what we would call 3 generations. So the up and down and the electron and its electron neutrino form the first generation. The second generation is the charm and the strange quark, the muon and the muon neutrino, and then the top and bottom quarks and the tau neutrino. Now, how do we find all of these, particularly since we as matter beings are actually only composed of up-down quarks and electrons? So where do those other particles come in? Well, they've been discovered through particle physics experiments over the last 30 years. And the top quark was the last quark to be discovered actually in 1993 at the Tevatron, which is a particle accelerator in Chicago. Now, in addition to these, 6 quarks and 6 leptons, there's actually also a whole other mirror side to this matter model, where we have what are called antiparticles associated with each one of those. And the antiparticles basically have almost this, well, they have the same mass. Usually if the particle is electrically charged, then their antiparticle has the opposite electric charge, and there can be other properties of them that are slightly different. But in general, they look the same. They're just like a mirror image of each other. In addition to that, there's one more family of particles that we know of, and that's where the gluons that I mentioned before fit in, and that's through the mediators of the 4 fundamental forces of nature that we've been able to discover. The one that you're probably most familiar with is gravitation. If you let something go, it falls to the ground. And that force, we don't yet know whether it has a particle level connection, a subatomic level connection. It's actually the weakest of the 4 forces, which might be surprising since in your everyday experience it probably feels like the strongest. But the second weakest fundamental force here is actually what's called the weak nuclear interaction. And it's mediated by a triplet of particles that was discovered at CERN in the late 80s and early 90s called the W and Z bosons. And then coming up in strength to the next interaction, we have electromagnetism, and photons are the mediators of electromagnetism. And actually, that is the force that has more to do with your everyday life than you would ever believe. But all of the interactions that you have with matter sitting on that chair right now is actually electromagnetic interactions between you and the particles in the chair are what are keeping you where you are. The strong nuclear interaction is the strongest, hence its name. And it really governs the clustering of nuclear matter at the heart of all nuclei, which is at the heart of atoms. And that's the field that I study at the particle accelerator at CERN. I want to also mention briefly the phase model of matter. So we talked about the particle model of matter. There's also a phase model of matter, and this one you're probably pretty familiar with. Solids, liquids, and gas, where here I'm showing just examples using water. You may have possibly heard about some other exotic kinds of phases of matter as well, but you don't necessarily experience them in your everyday life, except now I have to amend that statement because pretty much all of you have cell phones in your pocket with liquid crystal displays. So liquid crystal is actually another phase of matter, somewhere between a solid and a liquid, that now we were able to discover this through scientific experiments, and now we've harnessed it for good or for bad, however you want to think about it, to use as technology. There's also another phase of matter called a plasma, which is going hotter than a gas. So you imagine taking water and boiling it into steam. The steam is a gas. If we went and applied even more heat to the gas, we could actually dissociate it into charged ions, so particles, hydrogen and oxygen atoms, but they would not actually have their electrons attached to them, so they would form something called a plasma, which is basically free ionized particles moving around. Now, if we look at how a scientist would view these phases and try and understand their properties, we typically put together something called a phase diagram. So where we plot one particular macroscopic variable like pressure versus another one like temperature, and we can chart out where in this phase space of possible pressures and temperatures does this particular material exhibit certain properties. So where is it a solid, where is it a liquid, and where is it a gas? And basically through the course of observations, we can chart this out. It turns out that nuclear matter also has a phase diagram, and in this case we plot for our diagram temperature on the y-axis versus what I'll call matter density on the x-axis. And in the very early universe, we believe that the matter density was actually very low, and that the temperature was very high. And somehow, we ourselves and the whole universe evolved from that state to one where the temperature is relatively low, the matter density is sort of in a middle range, and that's enough to make atoms form, and then things stick together, and somehow we come out of that picture. But there's a lot of interest in understanding the properties of what I call the quark-gluon plasma. So this high temperature, possibly high density phase of matter, and understanding exactly what the interactions between those particles are in order to understand how they clump together and form atoms and eventually lead to us. So this is sort of a particle physicist model of the history of the universe, where the sort of far end here is today, where we are, and as you go back in time, you compress the size of the universe and heat it up. It's hotter earlier in time than it is now. And there was a phase back at the beginning, about a microsecond or a millionth of a second after the Big Bang, where it was made of quark-gluon plasma. So we can actually take particle accelerators, create this matter, and then try and understand how it evolves back into the matter that we're made of. There's a lot of lingering mysteries in particle physics. So we've actually built what we call a standard model of particle physics to describe everything that we've so far been able to measure. And for the most part, it's been, first of all, extremely successful. And so making predictions, and then we go out and we make an experiment, and we find what they predicted. But some of the pieces of the puzzle are still missing. And so one of the big pieces that the CERN Large Hadron Collider was built to try and answer was, why do we have mass? And there's a particle called the Higgs boson, which was predicted in 1964 but hasn't yet been observed because we don't know its properties. So we haven't known exactly where to look for it. But the theorists have made hypotheses about where it should be, what it should look like, how it should interact with other particles. And that's given us enough information to build an accelerator that can search for it. And so that's what the CERN LHC is about. Another aspect of the LHC program and trying to answer questions in particle physics is, what is the nature of dark matter? It turns out when you look with telescopes or with all possible methods of measuring what's out there in the universe, we find that about 25% of the universe is made up of invisible matter that we can't see, so we don't know what it's actually made of. And so people would like to know. And so one of the possibilities is with particle accelerators, you might be able to create particles that you would understand then are that constituent of the universe that is invisible to us. Another big question, the antimatter. So I mentioned on that previous image, oops, we'll go back here, that during the early universe, the matter density was very low. And what that means really is that there were equal parts of matter and antimatter right after the Big Bang. And now we don't know where that antimatter went. So there could be interesting properties of antimatter particles that make them somehow so that they have disappeared from our everyday experience. They're not part of the visible universe that we see as much as they should be, given what we understand about how the Big Bang happened and how the universe evolved from that. And so these are sort of some of the questions that we're trying to explore. And lastly, just looking at the properties of this quark-gluon plasma, as I said, to investigate how did we evolve from this early universe to this state that we see the universe in today. So the way we've done this, and this is where I bring back a tie to the theme of connections in this talk, is that these are questions that are bigger than one person can answer. And so it takes a lot of people coming together with the same purpose to try and solve the problems and answer these questions. So CERN is actually an acronym in French, although they've changed the first word. It used to be Conseil. Now it's l'Organisation Européenne pour la Recherche Nucléaire. So CERN. Basically, that means the European Laboratory for Particle Physics. It was founded in 1954. It's actually one of the first European endeavors after World War II, where everyone said, let's do something positive together. So it was actually an important way for all of the countries to kind of bury their hatchets and move forward. There are currently 20 member countries, most of them from Europe. Outside of the main entrance of CERN, you see all the flags from all the member countries hanging and waving in the wind out there. And more than 10,000 scientists have worked or are working at this laboratory. And more than 1,000 of those come from the US. So students from Cal Poly have actually participated in work at CERN, and that's true across the globe. So we make connections with people who are interested in answering these questions and basically coming together at a place where we can, where they have the resources and the technology to do it. So on that, welcome to the Large Hadron Collider. The Large Hadron Collider is a 17-mile circumference ring buried about 50 to 100 meters underground in the French and Swiss countryside. The French-Swiss border actually kind of comes right through the, not quite the middle, about the right-hand third of this is in Switzerland, and the other 2/3 are in France. You see up at the top Lake Geneva. It's just outside of Geneva, as I said, on the French-Swiss border. And the actual laboratory itself is this little wedge down here. And then the Large Hadron Collider is the ring that goes around like this. And you'll notice, if you look, this is just drawing a schematic of the ring on top of the landscape there, that there are communities and towns that are resting or existing on top of this accelerator that's buried underneath them. And so you can actually, it's kind of interesting. The experiment I work on is called Alice, and it sits in here. And you drive through a residential neighborhood, sort of turn a few corners, and then you approach a gate, an access gate, and you go inside, and you're at one of the experiments. It's quite amazing. Underground, what it looks like, it's basically a tunnel that's been hollowed out in the bedrock there in Geneva. And there's room in there for people to move around. They actually have little bicycles for the technicians who need to get from one place to another. That little path you can see with the white line on it is the bike path. If you need to do some repair work, you could go all the way around the 17 miles if you wanted to. I don't think very many people have done that, though. The actual accelerator itself is this blue tube you see here. And the particles are actually inside of a beam tube that's inside of this pipe that's only about a few centimeters wide. So it's a very small pipe where the particles travel. They're going pretty fast. There is a speed limit to the universe. Nothing can travel faster than the speed of light. And the symbol we use for that is c. And if you put it in terms of miles per hour, it's 670,616,629 miles per hour. And so the particles that we accelerate in the LHC are close to that. They're 99.99991% the speed of light, which amounts to just a difference in the last 3 digits of that speed. So they're going very, very fast. And the reason we want them to go that fast is because we want to collide them so that there's a very high density of energy in that one single location where the collision occurs so that we can liberate or create new particles out of that energy. It might sound scary or frightening, but it turns out that the macroscopic amount of energy in any one collision is about equal to the collision of 2 mosquitoes in flight. So it's, on a macroscopic scale, not much. But what makes it useful and interesting for particle physics is that it's condensed down to such a small space that the density of the energy is very, very high. So here's a cute little shot of sort of a cartoon rendering of what happens inside the collider. There's actually multiple accelerators, so each one of those rings represents a different accelerator, which speeds the particles up to their the maximum speed for that ring before they're injected into the Large Hadron Collider, two beams going in opposite directions. And then the particles collide, are basically brought into collision inside of these detector locations. And then what you're seeing here is the pattern of particles created in the collision and the detectors that measure them. So as I said, there's 4 experiments deep underground. The experiment that I work on is called ALICE, or ELISE. The Europeans, we have to usually try and distinguish Atlas from Alice. If you say them too fast, they sound the same and people get confused. So we say ALICE over there to make sure people know which one we're talking about. Here, ALICE is an acronym. Actually, all the experiment names are acronyms. And it stands for a Large Ion Collider Experiment. And we use Alice in Wonderland as our sort of mascot. So there she is at the top left over there looking through the rabbit hole at the particle collisions. But you'll notice that the size of the experiment is really quite immense. Oops, got it pointing the wrong way. So there's some people for scale. And it's 16 by 26 meters. A meter is approximately 3 feet, so you can do the math on how big that is. And weighs about 10,000 tons. And there's 18 different technologies inside of this detector. And different people have come together to build these different pieces of the experiment and then worked to fit them all together to try and understand what's going on in these collisions. And you might ask the question, well, why is it so complicated? How come you need all that technology to do this? And it turns out that you need different technologies because different types of particles interact differently. And if you want to know the most possible information about a collision, you want to gather as much information about all those particles as you can. So the typical components of a high-energy particle physics experiment are what we would call a tracking detector, an electromagnetic calorimeter, a hadron calorimeter, and a muon detector. And I won't explain too much about how they work, other than to say what kinds of particles they're sensitive to. So a photon, which is a particle of light, does not leave any trace in a tracking detector, because a tracking detector only sees charged particles, and photons are neutral. But it will leave a strong signature in an electromagnetic calorimeter. An electron, which is a charged particle, will leave a trace in your tracking detector, so we give a solid line there, but it also leaves a lot of energy in an electromagnetic calorimeter. So if you have both of those two technologies, you can tell the difference between a photon and an electron. Now there's other particles. There's something called a charged hadron. Hadron is just a name for any particle that's made of quarks. So remember that an electron is a lepton and a charged hadron is made of quarks. A proton is an example. It will leave a signature in both the tracking detector, a weak signal in the electromagnetic calorimeter, and so you add on a hadron calorimeter to detect those. You also have something called a neutral hadron, so it doesn't have any electromagnetic charge, but neutral hadrons are also unstable particles. They tend to decay to other things. If you start with a neutral particle, it decays into 2 other particles. The products have to also be net charge neutral. So that means you get 1 positively charged one and 1 negatively charged one. So they will leave a signal, and they will be charged hadrons that you'll be able to measure in the other detectors. Finally, there's muons. Muons are like heavy electrons, and they interact electromagnetically because they're charged, so they make a signature in all of these detectors, but they're really hard to stop. In fact, if you put your hand out right now, you've got tons, well, tons is maybe a non-scientific term, we'll say several muons passing through your hand from cosmic ray interactions with particles in the upper atmosphere of our Earth. And they pass through anything, or nearly anything. It's very hard to stop them. So what you hope is that if you put a muon detector out here, none of these other particles gets through, then you would know that you had a muon. The last kind of particle, whoops, go the other way. The last kind of particle, very elusive. Oops, the neutrino. So elusive that you really don't see it at all in any of these technologies. And you have to use other means to discover them. And actually, another professor here at Cal Poly works on neutrino experiments, trying to understand the nature of neutrinos. And like I said, it's a completely different kind of technology. And I'll just mention that not only is it another professor here at Cal Poly, he's also my husband. So it takes a village to do this kind of experiment, literally. So this is actually a shot of most of the ALICE collaboration in 2008 before they closed up the tunnel and didn't let us down inside the cavern anymore. But they're all standing outside of the ALICE detector here, some of them on top, some off to the sides. And all of these people, and many more who are not pictured, contributed to making this experiment work. In fact, over 1,000 scientists, engineers, and technicians, including 200 students. And it's a global community of people, all dedicated to this experiment, from 31 countries and 5 continents, because actually the 2 Americas are included in that. In the US, we actually have about 53 people who are part of this 1,000 people here, and including Cal Poly. And that's how I lead to these slides, showing some Cal Poly students working on ALICE. And so these are just shots of people I've taken over there with me to do work during the summers over the last several years. And working in the ALICE control room this last summer, we actually had 4 people plus myself there. And there is actually a button. You can stop the accelerator if you need to. But he didn't actually press it. Okay, so it's all very exciting and grand and great, but what do we actually do on a day-to-day basis? And it turns out we sit in front of a computer most of the day because we have to collect and analyze all the data from this big experiment that we've built. And ALICE collects about 1.25 gigabytes of data per second. So think about the amount of space you have on your hard drive and how long it would take ALICE to fill that up. Okay, not very long. And if you just look, okay, 3,600 seconds in an hour times 24 hours a day times 30 days in a month, we collect 3.24 million gigabytes of information in a month. So that's a lot of data to sift through. So we have to do a lot of time writing computer algorithms that can tell us what's interesting in all of that data, and also match what we see with simulations. Here's what a typical nuclear collision looks like in ALICE. All of these lines you see here are basically the trajectory of particles coming out of one of those collisions. And we have to figure out how to recognize those patterns and then what kind of particles they are and say something about what happened. So we do that by harnessing global computing power. Again, it's not something I can do on my desktop computer in my office. I have to use resources that are distributed across the globe. And this just shows for ALICE where all of the data centers are that data analysis is going on. So we have people in Africa, in South America, North America. There's actually 2 sites, Lawrence Livermore Lab and Lawrence Berkeley Lab in California. Lots of them in Europe because that's where CERN is located, but also in Asia and the Middle East. I'm a scientist, and I always feel remiss if I don't put something of a data slide into a talk to say, we actually we take data, we do something with it, and I'm not going to tell you anything about these pictures other than to say that these are kind of the types of things that come out of sifting through all that information to find something. And then I present a plot like this to a theorist who can tell me what it means or help understand what it means and what it says about how the universe works. And the way we communicate our information to other scientists so that they know how to use that information is through publishing papers and also giving talks at conferences where scientists come together. And so this is an important part, communicating what we've learned. It's not just enough for us to go seek the answers to the questions if we don't tell other people about what we found. So there's more of the connections there. So now I'm gonna segue into my portrait of a mad scientist. You're probably familiar with some of these images, maybe have seen some of these movies before. But you know, the mad scientist is a very popular villain in science fiction. I underline that because I think it's in fiction that they are usually mad. And characteristics of this archetype, you know, maybe villainous or antagonistic, insane or eccentric, possibly an evil genius. The one that probably most people worry about for real scientists is that maybe they're a scientist so involved with their own work that they reach the point of obsession and they're unable to see sort of the dangers of what their work might bring. Maybe Dr. Strangelove is a good example of that. And sometimes they're well-intentioned people whose either their methods or the technology that they develop kind of turns them into accidental villains. Maybe Frankenstein is a good example there. So that leads me to the question of, well, are we all mad scientists working at the Large Hadron Collider? And some people might say that we are, and that propose the idea of these doomsday scenarios, namely that collisions at CERN could possibly pose a risk to life as we know it by creating a black hole that would swallow us up. Or another thing that I won't talk too much about, but a strangelet, which is just a type of matter that would also suck up all of life as we know it, and we would all cease to exist. It turns out that's not a new question. People have been asking that same question about particle accelerators every time we build a new, bigger, more powerful one. And so the first experiments that I worked on at the Relativistic Heavy Ion Collider, which is in Long Island, New York, people were also worried that it would destroy life as we know it. And what the scientific community's response to this is that we presented our evidence based on independent scientific commissions who looked into the possibility and found no cause for concern. But you might say, well, how do you trust these possible mad scientists themselves who are making up these independent commissions? And you also probably wonder, where do questions like this come from? Well, in this case, they start with actually a scientist saying, I wonder if the LHC could create a black hole. What would be required? And they do some calculations and they write a paper and they submit it to the literature. And sometimes these things leak out into the popular culture and somebody latches onto the idea and blows it out of proportion. And that's actually what happened a few years ago. And I would really like to show this, but it's about 6 minutes, and then I have maybe 1 or 2 slides after that. Do we have time? Okay. So this is a kind of nice little clip from The Daily Show. I'm going to pull it up in my browser. From 2009, so you can actually go and see it online. Oops. Do we have it? Oh, it's not. There we go. Hang on. Okay. So the adapter wasn't totally plugged in. Are we ready?
Scientists.
There we go.
Well, we assume they're working for the benefit of humanity, but does their quest for understanding have a dark side? According to John Oliver's investigation of the world's largest particle accelerator, the answer is a chilling. Right!
The Large Hadron Collider promises to reveal the smallest building blocks of nature by recreating conditions that existed moments after the Big Bang. This begs the question, why the would you recreate the Big Bang? Does that not sound a bit dangerous? I sat down with pioneer particle physicist and experiment leader Dr. John Ellis.
Why do you want to destroy the Earth? We don't, and we won't.
Clearly, this evil genius was up to something.
Evil genius says what?
You're getting incomprehensible.
Evil genius says what? No, I need you to say what. And then I'll get you.
What?
I knew it. Evil genius.
Dr. Ellis seemed all too eager to explain away the dangers of his experiment.
The universe has been bombarding the Earth, the Sun, and the stars with cosmic rays which have much higher energies than the collisions we're going to make with the LHC.
Oh, yeah? How many Kelvin is that?
Kelvin is a measure of temperature, so we're talking about particles which have energies.
Do you even know what a Kelvin is?
Yeah, I know what a Kelvin is. Do you know what a Kelvin is?
I think I know what a Kelvin is.
I see. So what is a Kelvin?
I know what it is.
Tell me.
It's refracting the... I know what it is.
I'm listening.
Yeah, I'm listening. We're both listening.
Let's have a little bit of fact-based discussion here.
Yeah, let's do it.
So, Kelvin is a unit of temperature.
It's a unit
measured
of temperature
above absolute zero.
Above absolute zero.
Which... Go ahead, I'm waiting for you.
Which is cold.
Cold.
Evil genius says someone was getting a little defensive.
Nobody with any expertise in physics or astronomy or astrophysics thinks there's the slightest risk of any danger whatsoever.
Oh, really? What about this guy?
When we slam two atoms together, some theories suggest they might collapse into a micro-black hole, and eventually it would convert the Earth into a black hole.
That's Walter Wagner, the one man with the courage to speak out against the experiment, and he knows a few things about physics.
I teach a wide variety of science classes, primarily at the high school.
So, roughly speaking, what are the chances that the world is going to be destroyed? Is it 1 in a million, 1 in a billion?
Well, the best we could say right now is about a 1 in 2 chance.
Hold on a second. Is 50-50?
Yeah, 50-50.
There is 0% chance.
It's 50-50.
Zero.
Looked like it was time for a science off. Ellis tried to dazzle me with his childish scribbles.
So two of them may collide and make a Higgs boson.
While Walter continued to elucidate the Wagner principle.
It's a chance. It's a 50-50 chance.
You keep coming back to this 50-50 thing. It's weird, Walter.
Well, if you have something that can happen and something that won't necessarily happen, it's going to either happen or it's going to not happen. And so it's the best guess is in 1 and 2.
I'm not sure that's how probability works, Walter.
So who was right? The world-renowned theoretical particle physicist or Walter? Only one way to find out. Let the media decide.
Walter Wagner is haunted by visions of apocalypse.
This experiment could create a black hole.
According to Walter L. Wagner, might even create a black hole.
It could end up destroying the world.
But don't worry, Wagner has a plan.
I filed a lawsuit in the Honolulu court system.
Yes, it's just the latest in the pantheon of landmark Hawaiian court cases, such as Ho v. Asteroid, Man v. Pineapple Daiquiri, and the seminal Joe v. Volcano. But what if, by some slight chance, Wagner's Hawaiian lawsuit didn't work? I headed to the Doomsday Machine's home base, just outside of Geneva, Switzerland. The signs of evil intent were everywhere, from scary symbols to intimidating retinal scans to ominously rounded corridors. And suddenly there it was, the Collider itself. Clearly these scientists were up to no good. There was shiny machinery I didn't recognise everywhere I looked.
So when is this massive metal penis going to go into the gigantic metal vagina?
About the end of May. We'll move everything together. There's one the other end as well.
One in the front, one in the back. Ooh! Ooh! That's rude, actually. I wish I hadn't said that. And you shouldn't have high-fived
I shouldn't have high-fived you there, no.
I'd seen enough.
How safe is this place?
This place is perfectly safe.
Then why are we wearing hard hats?
It is safe for safety. We're wearing safety helmets.
Checkmate. With the Collider set to go online in weeks, it looks like everyone is doomed. Everyone, that is, except me and Walter.
Walter, if we're the only two humans left on Earth, we may as well try breeding, right?
Well,
it's worth a shot, is what I'm saying.
No, it's not worth a shot.
Well, I think you never know. Like you say, there's a 50% chance it'll work.
No, there's a 0% chance it will work.
Let's not argue. I don't want my last words in this life to be, "Oh, shut up, Walter."
So, as you can see, like I said, occasionally people get an idea about you know, how something reaches the popular culture and gets picked up on, and the mad scientist view of what we're doing seems to lead our imaginations beyond where they really should go. And as John Ellis said in that piece, really the way that the scientists, the possibly mad scientists I mentioned before, commissions explain this is that, you know, we look out at the universe itself and we just see no evidence that anything as catastrophic as a black hole that would destroy life, that could occur. And nature's laboratory is really cosmic rays. So the universe, as I said, is full of high-energy particles flying around, and sometimes they hit the upper atmosphere and produce a shower of other particles that come down and reach the ground. What you're seeing here is just an artist's rendition, but you can imagine that basically all the time we're being showered with these cosmic rays. And the energies of these cosmic rays are many, many orders of magnitude higher than the collisions we're going to create in the LHC. If you just look at the age of the Earth and factor in the rate of cosmic ray collisions, we're actually seeing the Earth itself has experienced many millions of collisions just like the LHC would create. And in fact, the universe itself, across everywhere we can observe, conducts 10 million, and that's not a typo, LHC-like experiments per second. And from all of our astrophysical observations, we have not seen any evidence of something happening catastrophically. So that's what went into those reports from those scientific commissions. And I think we've been actually operating the collider for almost a year and a half now with no catastrophic events so far. So the other thing that people have fixated on in recent years about some of the dangers of these types of experiments are, could we create antimatter bombs? Angels and Demons, that's Dan Brown's popular book that was also a film a couple of years ago. The basic plot, if you're not familiar with it, is that the Illuminati, a legendary secret society, are out to destroy the Vatican by stealing some antimatter from CERN and then using it as a bomb. And some of the facts around antimatter. This picture is from the book cover. This is actually from the film showing the canister, supposedly, that they were holding the antimatter in that they took to the Vatican. You would need, and in the movie they posit, they had about 1/4 grams worth of antimatter, which doesn't sound like a lot, right? Except when you say how much total antimatter has ever been created in CERN, and it's about 1/1,000,000 of a gram. So in all CERN is over 50 years old, and in all of that time, we've only created 1/1,000,000 of a gram, so I don't think it's a likelihood. It's also not portable, and I say yet because maybe they would come up with technology that would make it portable, but at least right now, the experiments on antimatter at CERN are, you know, the size of small cars. So they're not going to be able to put it in a backpack and take it on a plane to Rome. Some people have also wondered whether or not antimatter would be useful as an energy source if there's so much power in combining matter with antimatter. And it turns out, again, that it takes a lot of energy to create antimatter. So, you know, all of the money spent in making that 1/1,000,000 of a gram at CERN, it's really not a viable energy source. So this is sort of the second to last slide. So humanizing the mad scientist. In reality, we are obsessed with the work we do, sometimes to the point of developing eccentricities that make us less than good socializers. And so, you know, this is basically probably the highlight of these people's lives, is staring at this bank of computer screens 2 years ago when the first collisions at the collider took place, or a year and a half ago. But I stress that we have families and friends. We do what we do for the love of the search. We're not making millions of dollars off of what we do. That's not why we do it. We care about the environment, and we care about our legacies and impact. We have children. We're bringing in a new generation. So none of us really wants to destroy the world. So here's my concluding thoughts. I would say there's many ways to explore what it means to be human, and I've just presented one perspective, and it's that of a practicing scientist. So I think about the world in a particular way, and you may think about it differently, but I think that gives us a chance to talk about how we see things and maybe learn from each other, make more connections. I see scientific inquiry as a path to universal truth, as I say, a way to understand our place in the universe, to help contribute to human advancement. I get to leave a bit of a lasting legacy in the work that I've done, and also connect with this global community of people who are all also working for the same answers. And I think, kind of tying it back to the connections, we can think of the human being as an island of self, and maybe our next speaker will say something about that, but this is how I think of it, that we're really an island unto ourselves, and we need to connect to other people. And we do that by creating relationships, and also by creating the world we want to inhabit. And so in all of the actions that we do, that's what makes us human. So that's where I'll leave it, and I'd love to hear some of your thoughts too. Thanks for listening.